Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, East of Aeronautical Engineering. Today we'll discuss a topic in refrigeration and air conditioning, which is a subject for 7th semester mechanical engineering students. And the topic is vapor compression refrigeration cycle or vapor compression refrigeration system, which runs on a cycle known as vapor compression refrigeration cycle. Before going to the topic, we'll see first what is a refrigerant. So the refrigerant is nothing but a fluid which is suitable for refrigeration purposes. Now, how can you say that which fluid is suitable for refrigeration? Say suppose in this diagram, it is shown, this is a chamber which is being refrigerated. This the big chamber is being refrigerated or which is kept under which is to be kept under low temperature, say suppose at 2 degrees centigrade. Now, if I have a substance or a refrigerant which have a boiling point, okay, which is having a boiling point at 1 atmosphere. Okay, this is the room is at 1 atmosphere, and similarly the refrigerant is also kept at 1 atmosphere pressure, and at this at this pressure itself, the refrigerant is supposed to boil. Okay, or the boiling point temperature, boiling pressure, the vapor pressure of this refrigerant should be the atmospheric pressure or lower than that. In such cases, the substance is or the fluid is suitable for refrigeration purposes, and such fluids are called the refrigerants. So here what is happening here is, here we are keeping one one container called evaporator. So in evaporator what is happening is, the refrigerant is getting evaporated. Okay, in evaporator, the refrigerant is getting evaporated, and it is happening at the pressure which is equal to atmospheric pressure, or it can be lower than the atmospheric pressure. So, okay, that we will see in the future steps. So here the R12 is taken as refrigerant, and in case of R12, the atmospheric pressure, at atmospheric pressure, even the the refrigerant, it boils at minus 29.8 degrees centigrade. Okay, at 1 atmospheric pressure, even the refrigerant is at minus 29.8 degrees centigrade. The refrigerant will start boiling. How it boils? It will take the heat from the refrigeration space. Okay, so this is the refrigerating space, and from this space it absorbs heat and it will boil. Okay, so that even it will be converted into vapor, and this vapor is left to the atmosphere so that the pressure inside the chamber is maintained at 1 atmospheric pressure. Okay, so when this vent is open to the atmosphere, the pressure inside this is remaining at 1 atmospheric pressure, and it is taking heat. See here, the space is maintained at 2 degrees centigrade. So even the space is maintained at 2 degrees centigrade, it is absorbing heat from the space, the refrigeration space, and it is the liquid is getting evaporated in the evaporator. So this is the purpose. We are using the refrigerants, or this kind of fluids are used for the refrigeration purposes. Now, say suppose I use a valve here. Okay, throttle valve here. So if I use the throttle valve, what happens is, the atmospheric pressure, the pressure inside the evaporator is more than the atmospheric pressure. So here the pressure is 1 atmosphere, the atmospheric pressure. When I use a throttle valve here, what happens is the pressure inside the evaporator is more than 1 atmosphere, Even at this case, the temperature, the liquid which is used as refrigerant, it will evaporate because the boiling point is the boiling point is more than the temperature of the fluid. Okay, so the temperature of the fluid is minus 1 degree centigrade and the refrigerant space is maintained at 2 degrees centigrade, and because there is a temperature difference, the heat flows from the higher temperature to the lower temperature, and because of that the liquid evaporates as it takes heat more than the as it is required for the boiling of the refrigerant. Okay, so here the fluid is at minus 1 degree centigrade, and as heat is added into that, what happens is it is crossing the boiling point and it starts evaporating and it will be evaporated. Okay, so now what is happening is even at higher temperatures you are able to keep the space at 2 degrees centigrade. Now we will see what happens if the temperature, the pressure inside the evaporator is less than the atmospheric pressure. So for that to happen, what we are doing is we are pumping out this, we are sucking the vapor. Okay, here some vapor is forming and we are sucking the vapor, and because of that some vacuum pressure or the pressure inside the evaporator is below the atmospheric pressure. When the temperature is below the atmospheric pressure, what is happening is even at minus 73 degrees centigrade, the the refrigerant gets evaporated. When it is getting evaporated at minus 73 degrees centigrade, what we can do is we can keep the refrigerant space at as low as a temperature of minus 60 degrees centigrade. So this is the next step. So first what we did, we kept the evaporator at the atmospheric pressure and we are able to maintain this space at minus 2 degrees centigrade minimally. Now as I reduce the pressure of the evaporator below the atmospheric pressure, what is happening is we are able to cool this space up to minus 60 degrees centigrade. Now here again we are leaving this leaving this vapor to atmosphere, but here since we are pumping it out, we are sucking it out and pumping it out, the atmosphere, the pressure which is maintained in the evaporator is below the atmospheric pressure. Say suppose now here the continuously the vapor, it is getting boiled and it is becoming vapor. Now on that vapor is getting sucked out. So what we have to do is we have to maintain the level of the fluid so that there is a continuous cooling inside the refrigerant space. So for that what we are doing, we are having some tank kind of thing and we are supplying the refrigerant to the evaporator as it goes below the required level. So this bulb, as it goes down, it will open this and the fluid will start going inside this. So as when this bulb is at the required level, there is a cutoff. The fluid will not flow inside the refrigerant. So in this manner, what we can do is we can maintain the refrigerant space at lower temperatures continuously without any intermission. So this is the reason why we are maintaining, we have to maintain the liquid level inside the evaporator. Now, say suppose there is a thermostatic valve. Okay, previously we have seen there is a level control valve. Now, what we are doing here is we are thermostatic expansion valve we are using. So, as the boiling happens, what happens is it this the thermostat that is kept here, it will sense the temperature. So now when the temperature is sensed, so that means the vapor is started forming and it is being sucked out. So in such case, what will happen, automatically this valve will be opened. So this is a thermostatic valve. As the temperature reaches the vapor pressure, and the vapor is getting sucked out, at that time only the valve will be opened and the fluid is continuously supplied through this pipe. I mean this piping system, and this piping system is called the evaporator here. Previously what we have seen, we have taken a container and we try to maintain the level based on the volume control. Now here, when we are using a piping system, what we are doing is we are using a thermostatic valve which senses the temperature here and opens the valve and allow the fluid flow through the pipe. Okay, now here it will start liquid, it will be flowing as liquid, and it will be taking what you say, the temperature in heat from this refrigeration space, and it will start boiling, and finally here it will be a vapor. Okay, it will start as a liquid here and it will be vapor at this space. So when the temperature at this point reaches the vapor pressure, I mean boiling point of the fluid, and it will gets evaporated, then only it will start, this valve will be opened. So initially the entire thing will be liquid. Now as the as it takes heat, at certain point the temperature at this point will be equal to the boiling point. So that time the liquid will start evaporating. So when the liquid start evaporating, it will be sucked out by this pump. Now in such case, where we have to supply the fluid. So as the temperature increases up to the boiling point, the thermostatic valve, it will sense the temperature and open the valve and allow the fluid go through the pipe, so that there is a continuous supply of the fluid and continuous extraction of the heat and continuous maintenance. Continuously the space is maintained at minus degrees. So it can be minus 60 or minus 30 based on the pressure what we are going to maintain inside the pipe. Now if I want to make it a cycle, okay, so till now what we have done is we are allowing the vapor to go into the atmosphere. So if I allow the vapor, the refrigerant the refrigerant into the atmosphere, what happens is we are losing the refrigerant. So instead of losing the refrigerant, what we can do is we can again pass it into the series of pipes. This series of pipe is known as condenser. Why we are calling it as condenser? We are taking the heat from the vapor and we are making the vapor to condense into liquid form. Okay, so here vapor is coming and here heat is being removed. We are blowing some fan or we are passing some cold water, so that the vapor is condensed into liquid, and that liquid is collected in this tank. Okay, so here the vapor is coming from the evaporator and it is getting condensed in the condenser, and it is being collected here, and again since we are pumping out, the pressure here will be more, and with this high pressure the fluid will flow through this evaporator, so that it will form a cyclic process. So when it is a cyclic process, the loss of there will be some losses in this refrigerant, but it is not completely lost. Okay, so this is a cyclic process, and this cyclic process is called the vapor compression refrigeration cycle, and the system which runs on this kind of a cycle is called vapor compression refrigeration system. Okay, so here what are the things that are there? One is the refrigerant is getting evaporated, and the vapor is getting sucked, so that the pressure is lower here, and that at high pressure the vapor is sent through the condenser, and in the condenser we are extracting the heat, or we are removing the heat from the fluid, so that it will become a liquid here, and a high pressure liquid is available at this place, and the high pressure liquid is automatically circulated in this circuit. So this is the vapor compression refrigeration system, or the system which is running on vapor compression refrigeration cycle. Now here I said there are two parts. One is high pressure part, and the other one is the low pressure part. So the figure is showing the two sides. I mean, whatever cycle where whatever system is there, it is schematically is represented in this system. I mean, in this diagram. So here up this left side of this is the lower pressure side, and the right side of this is a higher pressure side. Okay, so what is happening here is we are sucking the fluid, so the pressure is more here and the pressure is less here. Now here again the liquid is condensed and passed through the expansion wall. So the expansion wall, what happens is it will reduce the pressure. So when the pressure is reduced, again it will be a low pressure side. So this side is the low pressure side, and this side it is the high pressure side. So this here what is happening is it is the evaporator is taking heat from the place which we need to be kept at a lower temperature, and in the condenser what it is doing is it is giving heat to the cooling, some coolant which is circulated through this heat and heat exchanger, be it is a air blown or something, whatever is required. Okay, so this is the schematic representation of the VCR, vapor compression refrigeration cycle or system. Now, so what we'll do now is we'll try to analyze this. What is the performance of this, and how to evaluate the coefficient of performance of this cycle. Now again we'll use the ideal cycle, which is called the Carnot cycle. So if the VCR, the ideal VCR if I want to take, then it should be a Carnot cycle, or the Carnot, the vapor which is being circulated in a Carnot cycle. Okay, so if it is a Carnot cycle, so what is happening, what we have two constant temperature heat absorption and rejection, and two isentropic work compression and expansion. So if this kind of system is there, so what is this figure? It is the TS diagram, the temperature and entropy TS diagram, and this is the schematic of the this vapor compression cycle based on Carnot cycle. So it is not an actual vapor compression cycle, it is a ideal vapor compression cycle which is running on Carnot cycle, vapor compression system running on Carnot cycle. So what is the difference between ideal and this actual? In ideal one we have this turbine, and in actual one we have removed this turbine and we kept a expansion valve. We will discuss further. Now first what we will do, if refrigerant is working on the Carnot cycle, what is the performance. So because the Carnot cycle is the ideal one and it will have the maximum COP, so what we are doing is we are analyzing first the Carnot cycle when the Carnot cycle is used for the refrigerant. Now here this is condenser temperature and this is evaporator temperature, and this is compression and expansion. So we have the reversal Carnot cycle being operated here using the refrigerant. So what we are doing is we are rejecting heat in the condenser. So at this temperature we are rejecting heat to the atmosphere, and at the evaporator temperature we are taking heat from the refrigerant space. Okay, so the amount of heat extracted or the amount of heat absorbed in the evaporator is nothing but the refrigerating effect. Okay, it is the refrigerating effect. So in the problem, if they ask what is refrigerating effect, okay, or refrigeration effect, so what is the amount of heat absorbed in the evaporator? What is the amount of heat absorbed in the evaporator is nothing but the refrigerating effect. So if that is the case, then the one way to calculate the refrigeration effect is the temperature of the evaporator, the temperature of the evaporator into the difference in the entropies between inlet and outlet of the evaporator. Okay, this is the inlet of the evaporator and this is outlet of the evaporator. As heat is absorbed, so the entropy is the entropy is getting increased from 4 to 1. Okay, now what is the amount of heat rejected? The amount of heat is rejected from 2 to 3. So here when the heat is rejected here, the entropy is getting reduced. So it is S2 minus S3. So the entropy is getting reduced from 2 to 3. So it is S2 minus S3 and it is maintained at a temperature, constant temperature. So it is called the condenser temperature here and it is TC. So constant temperature is to be maintained in Carnot cycle. So the temperature of the condenser is maintained at TC and the temperature of the evaporator is maintained at TE. If that is the case, what is the net work done? So the net work done is equal to the work done in all the 4 process, the net work done or in all the 4 process, or it is also equal to, based on the thermodynamic principles, it is the net heat removed or absorbed inside the cycle. So this is the net work done on the cycle and it is the net heat removed by rejected. Okay, net heat rejected. So the net work done and net heat rejected. So either thing I can use. So here, so the net work net is equal to the amount of heat rejected. That also we can use. So what is the amount of heat that is being rejected? So it is the evaporator. So in evaporator, what we are doing, we are taking heat and we are adding some work and we are rejecting in the condenser. So the temperature, the evaporator temperature, it should be TC minus TE. The temperature, condenser temperature is higher and evaporator temperature is lower. So it is so this is minus and this is plus. So here the net work done is nothing but the net heat rejected. So the heat rejected QC is more than QE. The heat rejected in the condenser is more than heat absorbed in the evaporator. So it is QC minus QE. If that is the case, again here it is minus TE into S1 minus S4 plus TC into S2 minus S3. So it is equal to TE by TC minus TE. So this is the maximum coefficient of performance that any cycle can have. Okay, but it is having some limitations that we will see. Now, if I want to calculate in a different manner, say suppose in form of enthalpy. Okay, so if enthalpy, if I want to use, it is a QC, the amount of heat rejected is nothing but enthalpy at 2 minus enthalpy at 3. So here the enthalpy is getting reduced because heat is being removed. And now here in this case the heat is getting absorbed, so the enthalpy is increasing. So it is a H1 minus H4. So now what is the work? Compressor work. So the compressor work is nothing but the enthalpy here in compressor. What is happening is the enthalpy is going to increase. So it is 1 to 2. The enthalpy is increasing from 1 to 2, and in the turbine the enthalpy is reducing from 3 to 4. So the compressor work is H2 minus H3, and the expander work or the turbine work is nothing but H3 minus H4. So the what is the network? Network is nothing but the compressor work minus the expander work. Okay. So that is the network that we have to supply to this this cycle. So here this is on this side and this is on this side. I mean, this is on the higher entropy side and this is on the lower entropy side. So what happens is the work that the turbine can produce is less than the work that is required for the compressor. So even though I have an expander or the turbine, the amount of work I have to supply more than the work that is given by the expander. Since here it is the liquid side and this is vapor side, the work produced by the expander is very less when compared to the work required by the compressor. Okay, so that is the reason what we will do. We will remove this expander and we will put the turbine and we will put a expansion valve that we will see in the next slide. So here in this slide what we are doing is we are finding what is the net work. So the net work required by the cycle is the compressor work minus the expander work. Since here the compressor work is more than the expander work, we have to supply more work here. So if that is the case, what is happening here is H1 minus H4. This is the refrigeration effect. The amount of heat absorbed in the evaporator is H1 minus H4. So that is the refrigeration effect. Now the denominator is the net work, that is equal to H2 minus H1, the amount of work given in the compressor, minus H3 minus H4, the amount of work developed in the turbine. So that is the case. Now if I want to simplify this, how I can simplify this? I can rearrange the denominator. How to rearrange? It is H2 minus H3 in one bracket, and I can put minus H1 minus H4. Okay, minus of minus H1 minus H4. If I put like that, what I can do, I can take this numerator into the denominator and divide this. If I divide this with H1 minus H4, what will happen? This is H1 minus H4. This will get cancelled and I will remain with H2 minus H3 by H1 minus H4. So that is what is given in the formula. So this is the Carnot, the refrigerant. If it is working on a Carnot cycle, reversed Carnot cycle, this is the COP of the refrigerator. Okay. Now this is the called the ideal vapor compression cycle. Okay. Ideally, if I am using a vapor, a refrigerant vapor and working then it should be working on the Carnot cycle. Now, what is the how it is different from the actual vapor compression refrigeration system? So here, as I already told, this is the liquid side, this is the liquid side, and this is the vapor side. When I am using the liquid and try to extract some work, I will get very negligible work. So, but the equipment is size is too high. Okay, so the equipment size is too high, and I am extracting work is very less. So, very less work from very huge space. So, instead of that, what I am going to use is I am going to use an expansion valve, and this expansion valve is working on isenthalpic process. The turbine is an isentropic process. The isentropic expansion is removed by isenthalpic expansion. So isenthalpic expansion means here H3 is there and here H4 is there. Both enthalpies are equal. So the enthalpies, both the enthalpies are equal. That's why it is called the isenthalpic process. So this is the one deviation of the actual vapor compression refrigeration system from the Carnot cycle. So we will see the other one. So what are the other deviations? Now if you see here, if I compress from here to here, okay, if I compress from here to here, there are some remnants of liquid inside this. So when there is a remnants of liquid inside this, what happens is the compressor performance will go down. So if it is a pure gas, the compressor performance will be high. So what we are doing is, for the same work, what it will do, it can go up to here. If I use so what I am doing is, I am in the evaporator, I am taking heat till a point that it is becoming a saturated vapor. Okay, I am taking the heat from the refrigeration space in the evaporator till the refrigerant reaches the saturation point. This line is called saturation vapor line, and this line is saturation liquid line. So here the evaporation is happening till it reaches the saturated vapor line. So what happens is, it is getting compressed to this point. Now what is the deviation here? Now if I see the condenser temperature in ideal cycle or Carnot cycle, it is a constant one. Now if I see the actual vapor compression system, what is happening in condenser is, the temperature is changing but the pressure is remaining constant. So the pressure is remaining constant but the temperature is changing. So the isothermal heat exchange is replaced by isobaric process or constant pressure process. So the constant temperature process are replaced by constant pressure process in actual vapor compression system. So these are the two deviations from the actual ideal cycle. So what is the one? One is the isentropic expansion is replaced by isenthalpic expansion. The other one is I am replacing the isothermal process 2 to 3 and 4 to 1 with isobaric process or constant pressure process 2 to 3 and 1 to 4 or 4 to 1. So these are the two deviations from the actual vapor compression system from the ideal vapor compression system. Now here you can okay, now we have discussed what is the working of the actual vapor compression refrigeration system. Now what we will do, we will try to analyze the actual vapor compression refrigeration system. Now as in the case of the previous one, in condenser the temperature is getting reduced, the enthalpy is getting reduced from here 2 to 3. So we don't have to bother about the temperatures here. Directly we can take the enthalpies and find out what is the heat rejected in the condenser. So that is the reason what we have seen both ways. One is the temperature and entropy, how to find COP in terms of temperature and entropy, and how to find the COP in terms of enthalpy in the ideal case, so that we can compare those two. So now here the heat rejected in the condenser is from 2 to 3. So if I know what is the enthalpy at point 2 and what is the enthalpy at point 3, I can find out what is the amount of heat rejected per kg of the fluid. Now, what is the refrigeration effect? So the refrigeration effect is in the evaporator, the enthalpy is changing from 4 to 1. Okay, it is increasing from 4 to 1. So the refrigeration effect is nothing but H1 minus H4. Now what is the network? Now we don't have any turbine. So whatever work is to be given to the cycle is given to this compressor. We don't have any work done by the turbine. So we have only the work given to the compressor. So that is the net work given to the cycle. Net work given to the cycle is nothing but the net work given to the compressor, so that the enthalpy is changing from 1 to 2. So it is increasing from 1 to 2. So it is H2 minus H1. So this is the network. Network is nothing but the work of the compressor. So now what is the refrigeration effect? So the refrigeration effect is nothing but the H1 minus H4. This is the refrigeration effect. And what is the compressor work? It is nothing but H2 minus H1. So that is giving the COP of the actual vapor compression system. Now in problems, what we'll need to find is what is H4. Okay, H4, what is the dryness fraction of the H4? Sometimes they will ask in the question. Now in the expansion process, what we are taking is H3 is equal to H4. H3 is equal to H4. H3 is on the saturation line, so it is easy to find. Now what is H4? H4 is here I have a saturation point. This is saturation liquid and this is a saturation vapor. So if this is this point, at this point the enthalpy is nothing but HF4. Okay, at this point the enthalpy is nothing but HF4, the enthalpy of the saturated liquid at this temperature. So it is, I am taking it as a HF4. I know what is H4. H4 is nothing but H3. So H4 minus HF4 is nothing but H3 minus HF4, and denominator is what is the difference in enthalpy between these 2 points. What is that? It is H1 minus HF4. If I use this formula, I can find out what is the dryness fraction at point 4. So this is the one point, side point, that we need to remember for solving the problems. Now there are other things that we need to find. What is the refrigerating capacity of the plant? Say suppose I am given the mass flow rate of the refrigerant. So the amount of refrigerant that is being circulated per unit time, the mass flow rate of the refrigerant is given. In that case, and I know what is the refrigeration effect, the H1 minus H4 are taken from the table, and I find what is the refrigerating effect per unit mass, and I know what is the mass flow rate from the problem. I can find out what is the refrigerating capacity of this system, the vapor compression refrigeration system. So if I multiply these two, I will get the refrigeration refrigerating capacity of the this system, VCR system. Now, what is the power consumed by the system? That also sometimes they will ask. So, I know what is the work done per unit kg. Work done per unit kg is nothing but H2 minus H1. Whatever enthalpy increased inside the compressor is nothing but the work done per unit mass. So, if I know what is the work done per unit mass, and if I multiply that with mass flow rate, I will get the total power consumption by the cycle. Now, sometimes they may ask you what is the amount of heat rejected in the condenser. So, amount of heat rejected in the condenser is nothing but mass flow rate into the enthalpy change inside the condenser. So, the enthalpy change inside the condenser is nothing but H2 minus H3, and the mass flow rate will be given in the question. If I multiply those two, I will get what is the amount of heat rejected in the condenser. Now, as we all know, what is the ton of refrigeration? Units of refrigeration is 1 ton of refrigeration. So, the 1 ton of refrigeration can be expressed at 211 kilojoule per minute. It can be it is equivalent to 211 kilojoule per minute, or it is also equal to 3.5167 kilowatt. So, the 1 ton of refrigeration is nothing but 3.5167 kilowatt. Says now, sometimes they will ask what is the mass flow rate per ton of refrigeration. So, what is the mass flow rate per ton of refrigeration required? So, I have the refrigeration effect, and this is the ton of refrigeration. So, the ton of refrigeration, 1 ton of refrigeration is equal to 3.5167. Okay. Now, what is this Q? I know what is the refrigeration effect. So, the refrigeration effect I know, and I want to find what is the, so what is this? This is the amount of heat rejected per kg of the fluid, and this is the total, this is 1 ton. This is 1 ton, and this is the refrigeration effect per kg. So, if I divide this 1 ton of refrigeration with the heat removed in the evaporator, it is nothing but the enthalpy increased in the evaporator, I will get what is the mass flow rate required per ton of the refrigeration in the plant. So, that is given by this formula. Okay. Now, if I want the power consumption per ton of refrigeration, so this is the mass flow rate per ton of refrigeration into the work done in the compressor, that is nothing but the change in enthalpy in the compressor, that is H2 minus H1. If I use these two, if I multiply these two, I will get what is the power consumed per ton of refrigeration. So, the power consumed per ton of refrigeration is equal to this is H2 minus H1, and QE is nothing but H1 minus H4, and that this already we have seen COP is equal to the refrigeration effect, that is equal to H1 minus H4 divided by the work done, that is equal to H2 minus H1. So, if I replace this, the power consumed per ton of refrigeration is inversely proportional to the coefficient of performance, and the constant of proportionality is nothing but the 1 ton of refrigeration. So, the 1 ton of refrigeration is 3.5167 divided by COP. If I do this, I can simply calculate what is the power consumption per ton of refrigeration. So, this is about the analysis of the actual vapor compression refrigeration system. And the textbook that I referred is the CP Arora Refrigeration and Air Conditioning by Tata McGrath. So, before concluding, we'll just review what we have discussed. So, vapor compression refrigeration cycle is based on a refrigerant whose boiling point is equal to atmospheric pressure or below the atmospheric pressure, less than or equal to the atmospheric pressure. So when the boiling point is the vapor pressure, or we can say at what pressure it boils, means it is the vapor pressure. If the vapor pressure of the refrigerant is below the atmospheric pressure or equal to atmospheric pressure, that kind of fluid we can use as the refrigerant. And if I use the turbine and compressor, and the condenser and the evaporator are maintained at constant temperatures, so what happens is it is the ideal Carnot cycle under which the refrigerant is working. So the refrigerant, if it works on ideal reversal Carnot cycle, then it is called the ideal vapor compression system. But the turbine here will work in with liquid, so this specific gravity will be very high and the work output will be very low, but the turbine space will be very high. So for that reason, what we are doing is we are removing this isentropic expansion in turbine with an isenthalpic expansion in an expansion valve. So that is one deviation of the actual vapor compression cycle from the ideal vapor compression cycle. So the other one is we are taking the we are increasing the enthalpy of the refrigerant in the evaporator so that it reaches the saturation vapor point. When it reaches the saturation vapor point and we compress it, it is going to be super heated. Okay, we will get a super heated vapor, and it is deviating from the condenser condition is deviating from the constant temperature process to a constant pressure process. So what we are doing is we are maintaining the condenser and evaporator at constant pressures in actual compression VCR cycle, and in Carnot cycle we are maintaining them at a constant temperature process. Thus that is the another deviation. So, and the analysis, if we understand the concept and represent in the TS diagram or HS diagram, where TH diagram, temperature and enthalpy diagram, and the temperature and entropy diagram. So, if I represent this in TS diagram, I can easily find out what is the COP of the actual cycle and ideal cycle. So, this is about the theoretical understanding of the vapor compression refrigeration system. So with that, I am closing the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.